Hello. So in this video, I want to talk about ordinals. Ordinals are important because they form a foundation for the numbers in mathematics, which I think we'll all agree are quite important. And they also let us define cardinals, which let us assign sizes to any set. And as with our previous videos, I will only use assumptions from the previous videos. So ordinals will be sets, and they'll be special type of set, and I will define what I mean by an ordinal. So what is an ordinal? Well, it's a type of set. So we say that a set alpha, it's common to use Greek letters to refer to ordinals. It is an ordinal if it satisfies the following two conditions. If one, uh, alpha is what's called a transitive set, this relates to the transitive condition in the previous video, is transitive. So this means, so this is a slightly new sense of the word transitive, but it's related to the other one, that for all x in y in alpha, we have x in alpha. So every element of an element of alpha is an alpha. In other words, the union of alpha is a subset of alpha. This is the equivalent condition to this one. And the second one is the one that makes it ordery. So we say we require that the set of pairs x, y in alpha times alpha. So this is the set of pairs of things in alpha such that x is an element of y is a strict well order. So recall a well order is a binary relation in alpha, so a set of pairs of things in alpha, which is reflexive, anti-symmetric, transitive. It's total in the sense that everything is comparable to everything, and it is well founded in the sense that every non-empty subset has a minimum element. And by strict, I'm just removing the reflexive condition. So it can be obtained from one of the things I just said by removing the identity, well, the set of the pairs which have the same thing in each entry. So these are like the best kinds of orders. The strict version compared to the non-strict version is like doesn't give you a lot of actual information. It's just sort of a technical thing. So I could have made it a non-strict well order by just adding in the pairs x comma x to this, and that would make it strict. And sorry, that would make it non-strict. Yeah. Okay. So this is an ordinal. So we have the definition. I want to prove a bunch of things about them, but before that, let's give you a little bit of intuition. So I'll give you some examples. So examples. First of all, here's my favorite example, which is the empty set. This is an ordinal. Certainly every element of the elements of the empty set is in the empty set because there aren't any. And this order is a strict well order because it's just the empty relation, which is a strict well order. So this is the first example. And this is how the number 0 is thought of by set theorists. So when we go on to define the natural numbers and all the other numbers, 0 will be defined to be the empty set. And we'll be viewing this empty set as an ordinal in this sense. So we can do usual ordinal things with it once we've established some more of those. And essentially, in some loose sense, all the other ordinals are constructed from this one, which we'll prove later. But for now, I just want to point out that the successor of any ordinal is an ordinal. So if alpha is an ordinal, then the successor of alpha, which I'm going to denote alpha plus, I use this notation in the ZFC axioms video. So this is defined to be the union of alpha and the set containing alpha. So this is the set of all things in alpha, and also including alpha. This is an ordinal. It's certainly a set. You can get that from the axiom of union and the axiom of pairing. And why is it an ordinal? Well, if I have an element of the set, it's either an element of alpha. I either have an element of alpha and I'm taking an element of that, which would then be an alpha because alpha is an ordinal, or I have an element of this part of the set. I'm like I've got an element of the alpha I've adjoined, and then that's in the set because I've got all the elements of alpha in the set. So it's transitive. And why is it a strict well order? Well, everything in alpha is comparable by assumption. and everything in alpha is comparable to alpha because it's an element of alpha. So this alpha we've adjoined is sort of the biggest element. If I have any non-empty subset, it either has some of the alpha elements in it, and so I just take the smallest one of those, or it doesn't, in which case it's just the set containing alpha, which has a smallest element. And you can write the details of that yourself. It's not too hard, but that's pretty much the proof that this works. So from this we can show that 0 plus is an ordinal, 0 plus plus is an ordinal, and so on. And this is essentially how we define the natural numbers when we get to the number system. So these are my first basic examples of ordinals. There are also infinite ordinals, which I'll talk about later. You'll notice that the axiom of infinity basically said there's an infinite set of ordinals if you phrase it now that you know this terminology. Okay, so the first thing we want to establish about ordinals is that you can order them. So not only are they ordered themselves, but you can compare them to each other. And you can compare them to each other in a very strong sense. So it turns out if I take any set of ordinals at all, which is not empty, I can find a smallest ordinal in that set. So if you look at the class of ordinals, which we'll show actually in a minute is not a set, but if you look at the class of ordinals, it's essentially well ordered in that you have any set of ordinals which is non-empty, it has a minimum element. And I'm going to prove that for you first. That's the first useful thing to know about ordinals. So theorem. If S is any non-empty set of ordinals, then not only does it have a smallest element, I'm going to tell you what it is, then the intersection of S. So I haven't used this notation before, I don't think. This is the intersection of a set. So this is the set of all elements, all sets which are contained in all elements of S. This is defined to be equal to X such that X is in S for all S in S. So this is the left S is a lowercase s. Let's write it like this. You can show this is a set using the explicit specification. You can pick the sort of domain set of this to be, I could write like union S here if I want, for example, so that I've got a set to specify from. But I can just pick any element of S as well if I wanted to. So this set here, I claim is actually an element of S. So the intersection of the set of ordinals has to be in it. In particular, it has to be an ordinal. And it's an element of all the elements of S other than itself. And for all alpha in S other than that one, we have this is in alpha. So this is going to be my smallest element of S. And it's quite cool. We can do this using just these properties shown so far. So, proof. Why is this true? So this requires a bit of setup. So, yeah. So first, I'm going to say I'm going to take an arbitrary element of capital S and show that it contains the intersection as long as it's not equal to it. So let alpha be an S other than the intersection of the things in S. And we show that alpha is indeed in, so the intersection is an element of alpha. If I do this, I'll have it's less than all the things in S, which is part of the statement, and it'll actually give me the rest of the statements once I fill with it a bit. Okay, so how do I show this? Well, first, which element of alpha is it? Well, I can figure that out. I can specify what it is. So alpha is an ordinal, so it's well ordered. So if I take any set of elements of alpha, I can find a smallest element of it as long as it's a non-empty set. So let let's say M for min. Or actually, let's use B for bad. Let B be the set of things in alpha which are not in the intersection. This is a set. I'm using the axiom of specification. and I claim that this is a non-empty set. Because if this set is the empty set, then that means every element of alpha is in the intersection, and everything in this intersection is an alpha, which would imply that they're equal. So note the intersection of S is a subset of alpha, because alpha is an element of S, and that's the definition of the intersection. So because alpha is not equal to the intersection, I know that alpha is not a subset of the intersection, which means B is not empty. Because if B was empty, then we would conclude that alpha is a subset of the intersection. Okay, so now B has the smallest element because it's a set of things in ordinal. So let M be defined to be the minimum value of B. This is well defined using the element of ordering on the alpha. On alpha, yeah. Because B is a subset of alpha. Okay, and now I'm going to claim that B is equal to this intersection. So claim so M is equal to this intersection. So M is equal to the intersection of S. I'm going to claim that two sets are equal, and I only have one tool for doing that, the axiom of equality. So I have to prove that every element of M is an element of the intersection, and I have to prove that every element of the intersection is an element of M. So proof of claim. So I'm going to prove a thing inside of a bigger thing. So let's take an element of M and show it's in the intersection. Let X be in M. Okay, well if X is an M, then it's an element of the smallest thing of the smallest thing, which is not in alpha. So first, because uh, X is in M, which is an element of alpha, and alpha is transitive, it follows that X is an alpha. And I know that X is less than M because the order on alpha is defined to be the element of thing, and I said X is an element of M. So X is smaller than the smallest thing, which is not in the intersection of S, which means it's in the intersection of S. So as X is not in B, we have that X is in the intersection of S. Because if it wasn't in the intersection of X, it would be in B. And it's not in B because it's smaller than the smallest element of B. Okay, so reversed, I have to show that everything in the intersection is an M. So let X be in the intersection of S, and I want to show it's in M. Okay. So okay. Well, as before, X is in alpha because it's in the intersection of S. So again, this is in alpha, which means it's either equal to M, less than M, or greater than M because alpha is totally ordered. So either X is an element of M, M is an element of X, or M equals X. Right now, I'm trying to prove that X is an element of M, so we can ignore this case because that's what we want. So I have to show the other two cases don't happen. So if M equals X, then that means I have an element of the intersection which is equal to the smallest thing, which is equal to like the minimum B. And X equals min B. And if we look at the definition of B, that means X is not an element of the intersection. which is a contradiction because I said it was. I said it was here. If x is equal to min b, then x is an element of b, and b is all the things not in the intersection. Okay, so if x is an element of, sorry, if m is an element of x, then I want to reach another contradiction. So in this case, uh, again, this means that, well, this means that m is less than x. These are both elements of alpha. And if m is less than x, that means x is bigger than the smallest thing, which does not contain the intersection, which is not contained in the intersection. Okay, so if m is less than x, then that means m is an element of x, and x is an element of the intersection of s. So for all beta in S, we have m is an element of x, which is an element of beta. Because beta is transitive, it follows that m is an element of beta. For all beta in S, which means precisely that m is in the intersection. Uh, but m is not in the intersection because m is in B, which does not contain anything in the intersection. So the thing's not in the intersection, which contradicts the definition of B. So this is a little B. So we are in fact in this case, the x is an element of m case. So claim is proven. Okay, so at this point I know that if I have any element alpha of big S, the smallest thing in alpha, which is not in the intersection, is in fact equal to the intersection. So corollary, so the intersection of S is an element of alpha for all alpha in S with alpha not equal to the intersection of S. Okay, and I remember I used the assumption that it was not equal to the intersection here when I said B was not empty. Okay, so what did I want to prove? I wanted to show that the intersection was in alpha for all things other than the intersection. And I also wanted to show that the intersection was an element of S. Well, this follows now because we need to show that the intersection of S, intersection of S is an element of S. Okay, well, if it's not, uh, if intersection S is not an element of S, then it follows from what I just proved, then it's an element of all the elements of S. Then intersection S is an element of alpha for all alpha in S. In particular, that means it's in the intersection because it's an element of all the elements. So the intersection of S is an element of the intersection of S. And this is a contradiction because of the axiom of foundation. You can also do this in other ways, but for now we'll just use the axiom of foundation. So thus the set just containing the intersection of S, this is defined by the axiom of pairing, contradicts the axiom of foundation because this has no elements which are disjoint from it. And we're done because we just shown that if the thing is false, we have a contradiction. So now we know that any non-empty set of ordinals, it contains its intersection, and all its other elements contain that intersection as elements as well. Okay. And this gives us that ordinals are comparable in some sense. So corollary, this is like a theorem which follows from a more important theorem. So if alpha and beta are ordinals with alpha not equal to beta, then either alpha is in beta or beta is in alpha. This follows from the previous theorem using the following set. So proof, apply theorem to the set alpha beta. This is a set by the axiom of pairing. It's a set of ordinals because we just define these to be ordinals, which means it contains its intersection. Its intersection is either equal to alpha or beta, which means either alpha is a subset of beta or beta is a subset of alpha. And moreover, the other one of the two contains the intersection as an element. This follows from the statement of the theorem. Okay, so now we have that if we have any two ordinals at all, one of them is in fact an element of the other one, and more of it's a subset of the other. So we can use this to define the notion of order on the ordinals. We denote alpha element of beta by alpha less than beta for ordinals alpha and beta. The previous corollary basically says this is a total order. It's transitive because ordinals are transitive. It's not reflexive because we're talking about irreflexive things. And no thing is an element of itself using the same argument given at the top of this page. And it's actually essentially a well order in this, because the theorem says that if I have any set of ordinals, it has a smallest element being the intersection of the set. So I basically showed now that the ordinals are well ordered in some sense. They're not actually a well ordered set because I haven't proved that the ordinals form a set, and in fact they don't. And that's the next thing I want to point out. But the corollary to these corollaries is that it's very easy to recognize if I have an ordinal. So corollary, if S is any transitive set of ordinals, then S is an ordinal. Okay, and why is this true? Well, I essentially told you why it's well ordered using the previous discussion. And it's transitive because I said so in the statement, which means it's an ordinal. An ordinal is just a transitive well-ordered set, which is well ordered by the element of relation, and this satisfies that condition. Okay, so I'll now give you a nice theorem which comes from this corollary. So the class of ordinals is a proper class, meaning that it is not a set. There is no set which contains all the ordinals. Okay, now proof. It's quite easy. Suppose for a contradiction that I have a set of all the ordinals. That S is the set of all ordinals, which I'm trying to show doesn't exist, then clearly it's it's a set of ordinals, which satisfies one of the conditions of the corollary. It's also transitive because we can show that in an element of an ordinal is an ordinal. Note that is alpha is an ordinal. And beta is an element of alpha, then it's a subset of alpha. That's essentially the transitive condition from before. Then beta is a subset of alpha because alpha is transitive. So it's a suborder of a well order, and so it is also well ordered by element of. Beta is also well ordered by element of. And any element of an element of beta is an element of alpha, and in fact must be less than beta because alpha is well ordered, and that means it's in beta as well. Beta is also transitive as alpha is transitive. and every element of an element of beta must either be greater than beta or less than beta or equal to it, and it cannot be greater than it, or we would not have a well ordering on alpha. Uh, totally ordered. So every element of an element of this set of ordinals is an ordinal. Every element of an ordinal is an ordinal, and it follows that the set of all ordinals is an ordinal by the previous corollary. So S is an ordinal because it's a transitive set of ordinals, which means S is an element of S because S is the set of all ordinals, which is a contradiction. A set cannot be an element of itself using the axiom of foundation. Okay, so we now have a proper class of ordinals, and this will be cool because ordinals are essentially going to describe size when we get to cardinals later on, and every size will correspond to an ordinal. So it makes sense that we can't put all the ordinals in a set because then we'd get like a size which is bigger than all the sizes, and that wouldn't make any sense for us. Okay. So the next thing I want to show is in fact that every set corresponds to an ordinal. And we'll do this using a notion of bijections, which I did not define in the previous video. So bijections give us a way of describing sets having the same sort of size. We will be able to biject any set to an ordinal, which will essentially tell us that we can order any set, which is what we want to prove. We want to think of ordinals as being representatives for all sets in some sense. So first definition, we say that a function f from a set x to a set y is injective if it never maps two different things to the same thing. If x not equal y implies xf is not equal to yf for all x and y in x. Surjective if it hits everything. If for all y in y there exists x in x with x f equal to y. So for every element of y, I hit it with something. So the first condition saying I never hit anything twice, and the second condition saying I hit everything at least once. So that we've got like at most once and at least once. And 3 is bijective if it is injective and surjective. And surjective. It is injective and surjective. So this says I hit everything in y at most once using things in x when I apply f. So that gives me a one-to-one correspondence between the elements of x and elements of y. This is, we could call this like a set isomorphism. It says that two sets are the same in terms of I can just sort of relabel the elements of one to get the other one. And I will show now that we can do this with ordinals. So theorem. If I have any set, if x is any set, then there is an ordinal alpha and a bijection phi from alpha to x. So for any set, I can find an ordinal which is in correspondence with x one-to-one and onto. So I can relabel the elements of x to just be the elements of the ordinal, and that's how I'll be able to order the elements of x. So this gives us sort of this tames the class of sets, which we previously had no real understanding of what was going on. It was all sort of big and vague as to what things exist. And everything that exists, we could just sort of relabel the things and get an ordinal. So this is a very powerful theorem. It's called the well-ordering principle, and it is equivalent to the axiom of choice, which was a controversial thing from before. I will now prove it from the axiom of choice. I won't do the reverse implication, but the reverse implication is actually easier. Fun exercise. Prove that if everything is well-orderable, then you can use the axiom of choice. So proof. And my proof will, of course, use the axiom of choice because you need to. Okay, so and I'll use all the other axioms too. So I'm going to construct this bijection phi and this alpha, which is its domain. Okay, so I need a choice function. So let P be the power set of X, which exists by the action of the power set. So this is the set of all subsets of X. I'm going to modify it a bit. So with the empty set removed. I can do this with the axiom specification. So this is the set of all non-empty subsets of X. So this P equals non-empty subsets of X. So this is a set of subsets of X. It's just a set of sets, and the sets are non-empty. So I can apply the axiom of choice. By the axiom of choice, I can now choose an element of all the elements of P. Let C from P to the union of P be a choice function. The union of P is just X. So for every element of P, every subset of X, I can choose an element of it using this function C. So it maps every element, every subset of X to one of its elements, every non-empty subset to one of its elements. Okay, I'm going to use this to construct my bijection. So basically, I want to use choice to choose what the bijection is. And to do this, I'll introduce a thing which I call a choice chain. So this is a definition. It's like a local definition. I won't be using this outside of the proof. So I'll say a subset of X is called a choice chain if it's constructed using the choice function and mapping ordinals to things. We say a chain is a word for a well order, which is, so these will be well ordered. In fact, chain is a word for total order. These will be total orders, and in fact, they will be well orders because I'm going to choose them to be really nice. Chain is just a general word for a total order. We define a choice chain to be a subset of X such that there is a choice chain isomorphism. This is the thing which is we order it. There is a choice chain. So there's a bijection phi a choice chain C phi C from some alpha C. So this is some ordinal to C where alpha C is an ordinal. And this map is order preserving in some sense. Now X doesn't have an order on it, so this might not make any sense. But by order preserving, I mean it's going to preserve the order I want to define on X, which will be defined using my choice function. And for all beta in alpha C, the smallest, so in alpha C, it maps beta to the smallest thing that's not already mapped to. I'm going to choose what the smallest thing is using my choice function. So for all beta and alpha, my function maps beta to what the choice function would choose it to map to. So is equal to the choice function applied to X without phi applied to the previous thing. So this is gamma phi C for gamma and beta. So I apply phi C to all the previous things in beta. I don't map it to any of those, and I just pick something using my choice function. So this is a non-empty subset of X, and I'm choosing an element using C. For this to make sense, it has to be a non-empty subset of X. It might, if the set was the empty set, we'd actually be done. You can see that this would mean we actually hit every element of X. But yeah, this is what a choice chain is. And I'm going to claim that I can basically make the whole set a choice chain, and that'll give me my bijection. Okay, so uh, important things about choice chains. They're essentially unique given an ordinal if there is a thing which does it. So here's a claim about choice chains. So And we call this phi thing a choice chain isomorphism. We call phi C a choice chain isomorphism. It's preserving the structure that I'm trying to define on the image from an ordinal. Okay, so if I have two choice chains, if C1 and C2 subset of X are choice chains, then they're comparable if and only if their corresponding choice chain isomorphisms are comparable. And in fact, these isomorphisms are unique. So this is and phi C1, phi C2 are corresponding choice chain isomorphisms. Then C1 and C2 are comparable if and only if these are comparable. Oops, in the same way. So essentially finding a choice chain and finding a choice chain isomorphism are equivalent. We'll use this to sort of make our biggest choice chain at the end. Okay. So proof. So why is this true? Well, one implication is actually quite obvious. So I'm trying to prove an if and only if. So I'll prove that the right thing implies the left thing, and then the left thing implies the right thing. So first I need to prove that if the functions are comparable, then the choice chains are comparable. This one's fairly easy to see. So if I have a choice chain for C1, a choice chain isomorphism for C1, and a choice chain isomorphism for C2, then C1 is the image uh, of this phi function. So this is so the image of phi C1 is C1. The image of phi C2 is C2. So I know the image of phi C1 is a subset of the image of phi C2. So if I'm in the image, I'm just the right half of a tuple in the thing. So this is preserved by going to image. And this, so then C1 is a subset of C2. So this one's pretty straightforward. I now know the easy implication. So but why is it the case that if I have two comparable choice chains and I have any choice chain isomorphisms for them, then they're comparable? This is harder. So now I suppose that C1 is a subset of C2, and I want to prove that phi C1 is a subset of phi C2. Okay. So we show that phi C1 is a subset of phi C2. This will imply that for a fixed C1, the isomorphism is unique, by the way, using containment both ways. Okay. Well, good thing about these choice chain isomorphisms, they're well ordered because their domains are ordinals. So I need to take an arbitrary element of phi C1 and show it's in phi C2. So suppose that phi C1 is not contained in phi C2. This means that the set of elements of phi C2, C1, which are not in phi C2 is non-empty. Then the set alpha x in phi C1 such that alpha x is not in phi C2 is not the empty set. Because if this was the empty set, then every element of phi C1 would be in phi C2, which means it would be a subset. Okay, now I have a non-empty set, and they're essentially ordinals. They're not quite ordinals because they have these sort of x's tied to them, but they're essentially ordinals. So if I look at there's like a smallest thing in its domain, which is not in the domain of phi C2. So we can define beta to be the smallest thing in the domain, the min of, say, the gamma in the domain of phi C1, such that its image is not in phi C2. So it's such that gamma with phi C1 applied to it is not in phi C2. This makes sense because this is a non-empty set, and this is a set of things in the domain, which is an ordinal, so it has the smallest element. And I know that beta is in the domain of phi C1. So this is well defined, is in X. And I know what it is because I told you what it has to be for a choice chain. Phi C1 has to map beta to the smallest thing, which is not in the image of the smaller things under phi C1. And moreover, I know that beta phi C1 is equal to choice applied to X without gamma phi C1 for gamma and beta choice. But I also know that beta, I mean, it has to be in the domain of phi C2 because C2 contains elements other than the image of the restriction of phi C1 to beta. So note this set here on the right, this set like without this set minus the thing that I'm taking away is not all of C2 because this set here is a subset of C1. And I'm trying to prove that C1 is contained in C2. So this is not all of C2. So beta actually has to be in the domain of phi C2. Because otherwise I would have hit everything in C2 already using the elements of beta. Otherwise, C2 would be equal to gamma phi C2 for gamma and beta, which is the same as phi C1 because the thing smaller than beta, they agree on what they do with both functions. Okay, so beta is also in the domain of phi C2. And now, because phi C2 is a choice chain, I know where it does, right? So also, as phi C2 is a choice chain isomorphism, I know that phi C2 beta is actually the same thing because I'm choosing from the same set is equal to X gamma phi C2, which is the same as phi C1 for these small gamma. And I apply choice to it, which is equal to beta phi C1, which is a contradiction because I just said up here that beta is the smallest thing where phi C1 and phi C2 disagree. This is a contradiction. Because phi1 and phi C1 and phi C2 have to disagree on beta. Okay, so I've just shown here that if two choice chains are comparable, then their corresponding choice chains isomorphisms are comparable in the same way. And this implies that for any fixed choice chain, the choice chain isomorphism is unique because any two things have to be contained in each other. So it follows that for any choice chain C contained in X, the choice, using a different notion of choice, of phi C is unique. And now I'm almost done. I want to get that the whole set is a choice chain, which will give me a bijection from it to an ordinal. So here's what I do. So we can now consider the set A, which is equal to the union of all the choice chains which exists using the axiom of union and specification in the power set. C is a choice chain. And I know that this gives me a corresponding set. So I'll define phi A to be the union of phi C, where phi C is a choice chain isomorphism. And this union here is actually a function, because if I have any two of these functions which agree on the same points, which like have the same point in the domain, they have to do the same thing by the previous theorem. Okay, so by the claim, if C1 is a subset of C2, then I know that phi C1 is a subset of phi C2. So if I have any two choice chains, C1 and C2 are choice chains, then I know in fact that their intersection is a choice chain. Why do I know this? Because if I take their intersection, I can pull back the isomorphisms to ordinals, and then one of the ordinals is smaller than the other one. As uh, uh, phi C1 and phi C2 are comparable because they correspond to ordinals. So either C1 cap C2 equals C1, or C1 cap C2 equals C2, which means now if I have any two choice chains at all, then their union is also a choice chain because the union is equal to one of them. So hence C1 cup C2 equals C2, or C1 cup C2 equals C1, which means now that I have the union of all the choice chain isomorphisms, this gives me a well-defined function. If I have any two things in its domain, one of them comes from a bigger choice chain than the other one, and they agree on these choice chains. So the function, so the relation phi A is in fact a function. Okay, now that I know that phi A is a function, its domain is A by definition. The domain of phi A is A. Phi A is injective because if it takes two things to the same thing, those things belong to two choice chains, one of which is, well, two ordinals, one of which is larger than the other one, and they have to agree on the choice function, the choice chain isomorphism corresponding to that ordinal, which was injective. If alpha and beta belong to the domain of phi A, then there exists a choice chain C with phi C subset of phi A and alpha beta in the domain of C, domain of phi C, because phi C is injective. As phi C is injective, it follows that alpha phi A is not equal to alpha beta phi A. Because this is equal to alpha phi C, and this is beta phi C, and these are not the same. This is assuming that alpha was not equal to beta, sorry. Alpha not equal to beta. Okay. So this is injective. Is it surjective? So uh, if phi A is surjective, then we're done. Because the domain of phi A is a transitive set of ordinals. Then we are done as domain phi A is a transitive set of ordinals and such an and is thus an ordinal. Transitive set of ordinals. So is an ordinal. And, and yeah, so we just need to show it's surjective. In fact, it is a surjection onto its image. So the image of this thing is a choice chain. So note, did I say that the domain of is the domain of? So I should just have the image of phi A is A, not the domain. The domain is some ordinal. Okay, note the image of phi A is a choice chain because it's phi A is a bijection from an ordinal to it. It satisfies the condition because it's a union of things which satisfy the condition. Um, uh, is a choice chain contained in X? With phi A being the choice chain order isomorphism. The choice chain isomorphism. Okay, so I'm now going to show that there's nothing else in it. So it suffices to show that A is equal to X. It suffices to show A equals X. If it's not, if A is not equal to X, then the domain of A is an ordinal, which has a successor, and X is an element in it, which is not in A. Then I can take X without A. This is a set, and it's not an empty set. I can apply my choice function to it. It is defined. So I can just take phi A, and I can union it with the pair. In the domain, I put the successor of its domain. If I just put its domain, I put the domain of phi A as the first entry, and then I put this new thing as the second entry. The domain of phi A is not an element of the domain of phi A. It's in fact it's the smallest ordinal not contained in the domain of phi A. It's because it's a set of ordinals and it contains all the things in the domain of phi A, and obviously nothing smaller than it does that. So this is a well-defined function. With domain dom phi A plus the successor ordinal of dom phi A, and it's a choice chain isomorphism because it has all the properties we require. I defined it to map the last point to where it's supposed to go, and it already mapped all the previous points to where it's supposed to go. So the image of phi A with this new point attached to it is a choice chain, and it's not contained in A because the set on the left is A, and I just chose a thing not in A to add to it, is not contained in A, which is a contradiction because A is the union of all the choice chains. And that completes the proof. So now we know that if I have any set at all, there is a bijection from that set to some ordinal. And we can use this by the axiom of choice. We essentially choose where we want the ordinals to go in order. And if we can't do this, there's like a smallest thing where it doesn't work. That's the gist of the proof, but here are the details. Okay. Now that we know that there's a for any ordinal, I can biject for any set, I can biject it to an ordinal. We can then start talking about cardinals in the next video. And then once we've got cardinals, we can start doing some operations with them, and that'll give us the numbers we all know and love. But yeah, let's stop there for today. Thank you.